Hi everyone, this is our second lecture on induction machines. Today we're going to develop an equivalent circuit for induction machines. Notice here we're not distinguishing between induction motors and induction generators because both are going to have the same structure and the same type of equivalent circuit. To develop a model for an induction machine, we first have to think about how it operates. Let's take the example of an induction motor. You connect the motor to the supply. Three-phase currents are going to flow into the windings of the stator, creating a rotating magnetic field. This rotating magnetic field will cross the rotor bars or windings and will induce voltages and currents into them. If you think about it, this is exactly the same as what happens in a transformer. In a transformer, you connect the primary to the supply. This will create a magnetic field which will then cross the secondary winding and will induce voltages and currents into it. So the essence of operation for transformers and induction machines are the same, despite the fact that one has rotation and one doesn't. So the equivalent circuit is going to be the same for both. Here you can see an example of an equivalent circuit for an induction machine. Notice how similar it is to a transformer. Here, on the left-hand side, I have Rs and Jx of S, which are the resistance and reactance values of the stator winding. On the right-hand side, I have Rr and X of R, which are the resistive part and the leakage inductance part of the rotor circuit. Similar to a transformer, I have core parameters. These consist of R of C, the core loss resistance, and X of M, the magnetization inductance. And again, similar to a transformer equivalent circuit, you're going to have an ideal transformer. Now for a transformer, defining the turns ratio for the ideal transformer would be easy. You just consider the number of turns in the primary winding divided by the number of turns in the secondary winding. This is a little bit different when you get to an induction machine. Typically, we define the turns ratio for an induction machine by dividing the number of conductors in the stator winding per phase by the number of conductors in the rotor circuit per phase. This, of course, is only applicable to rotors which have windings, wound rotors. If you have a squirrel cage rotor, you're not going to be able to define a turns ratio mathematically. So you're going to have to heuristically choose a number that best represents the performance of that machine. If you look at this equivalent circuit for the induction machine, you notice a big difference between this and what we have for a synchronous machine. Despite the fact that both are AC machines and both are three-phase, the equivalent circuits are going to be very different. One big difference is that synchronous machines are going to have an internal voltage source EA, which we don't have it here. This is because we don't have a field winding in induction machines. Despite similarities between circuits for an induction machine and a transformer, there are some differences in values. One in particular is related to the presence of air gap. An induction machine has an air gap, whereas a transformer doesn't. Air gap increases the reluctance of the flux path. This means that you're going to need higher magnetization currents in order to obtain a certain level of flux, which again means X of M, the magnetization inductance, is going to be very small compared to what we had for a transformer. Because of the air gap, we're going to have weaker coupling between the stator windings and the rotor windings, and the value of the leakage inductance is going to be higher. If you recall, when we wanted to solve a transformer problem, we used to refer all quantities from one side to the other. Ideally, we would like to do the same for an induction machine. We would like to take the rotor parameters and refer them to the stator side. However, when it comes to induction machines, things are a bit tricky. In a transformer, as you go from the primary side to the secondary side, the voltage level changes and the current level changes, but frequency stays the same. If you connect the primary to 60 Hz, on the secondary you're going to get 60 Hz as well. This, however, is not the case in induction machines. Not only the voltages and currents change as you go from the stator side to the rotor side, the frequency changes as well. You'll recall from our previous lecture that f of r, the frequency induced in the rotor circuit, is going to be s times f of e. In other words, it's a function of the speed. When the speed of the motor changes, the frequency of the voltages and currents induced will change as well. We can pretty much say the same about the voltage magnitude. Voltage magnitude induced on the rotor circuit, E of R, is going to be a function of speed, S times E of S. You can check this by looking at the boundary conditions, two extreme cases, when the rotor is running at synchronous speed versus when it's standstill. When the rotor is running at synchronous speed, S is 0. No relative motion exists between the rotor circuit and the rotating magnetic field of the stator, hence no voltages will be induced. S is 0, E of R will be 0. On the other hand, when the rotor is at standstill, it will see the rotating magnetic field of the stator rotating at a speed of synchronous speed, N of S, omega S. As a result, maximum voltages will be induced in the rotor circuit. In a situation like that, S equals 1, and ER would be the same as ES. Now, let's consider the circuit on the left-hand side. This is the rotor circuit. We have ER, which is the voltage induced in the rotor circuit, connected to RR, rotor resistance, and JX of R, the leakage reactance. I can write an equation for the rotor current. IR equals ER divided by R of R plus JX of R. Notice, however, this circuit is operating at a different frequency. It's operating at F of R. Now, what's the most important element in this circuit that is dependent on frequency? That would be X of R, the reactance. I can write X of R as L of R times omega R, L of R being the inductance, and omega R being the frequency. Now, omega R, or F of R, is going to be a function of the stator frequency. I can write this as S times omega E being associated with the stator. So I can write X of R as S times omega E times L of R. And then I rename that portion, omega E times L of R, as XR0. That 0 indicates that this is the reactance at the rated frequency at 60 Hz. Let's plug in this value in the equation for the current. So IR becomes ER divided by RR plus JS XR0. This is still indicating a circuit that is operating at a different frequency because I have that S multiplied by X. This indicates that the frequency is not omega E, is S times omega E. If I want to remove the effect of frequency, what I can do is I can divide the numerator and denominator by S. In the numerator, I would get ER divided by S. In the denominator, I would get RR divided by S plus JXR0. Notice now that the frequency-dependent term, which is a reactance, has no factor of S in it. So I can assume that this is similar to a circuit that is operating at 60 Hz. By doing this simple trick, I managed to convert the rotor circuit to a circuit that is operating at the same frequency as the stator circuit. Now I can simplify this a little bit more. ER divided by S is going to be the same as E of S. And RR divided by S is just a variable resistance. Notice in these equations, I ignored the effect of turns ratio. So for simplicity, I assumed that A, which is a turns ratio of the ideal transformer, is 1. So I don't have to worry about the prime notation. By doing this, I could actually treat the rotor circuit as a circuit on the stator side, and all the effects of variable speed on the frequency and the voltage are actually modeled in the form of a variable resistance, RR over S. Now, this circuit is ready to be referred to the stator side. The complete equivalent circuit is developed when I refer the rotor quantities to the stator side. Again, as I mentioned earlier in the previous discussion, for simplicity I assumed that the turns ratio is 1. But in practice, the turns ratio is going to be something other than 1. meaning that when I refer quantities from rotor side to the stator side, I have to add the primes. The full model is shown on this slide. On the left-hand side, you have the stator parameters, R of S, the stator resistance, X of S, the stator leakage reactance. On the right-hand side, you have the referred rotor quantities, RR prime divided by S and XR0 prime. Notice that this resistance is going to be dependent on speed, so this is not a constant resistance. And again, as I mentioned before, we're going to have the core parameters just like we do for a transformer. Notice a couple of things about this model. First, this is a per-phase model. So similar to what we did for three-phase transformers, every time you want to analyze this model, you would have to convert the quantities from three-phase to single-phase. Second important thing, notice the tildes on top of V's and I's. The voltages and currents are AC quantities and there are phasors. If you look at different textbooks, you might see different notations. Some, for example, for simplicity, instead of showing RR prime and XR0 prime, they show them as R2 and X2. And sometimes they replace RS and XS with R1 and X1. Regardless of what you do and what notation you follow, you have to remember what these quantities are representing. Some are representing the resistance of the metal bars and the resistance of the windings. Some are representing the leakage inductances. So it's important to pay attention to what they represent. Once you're comfortable with that, you can take any notation that you want. Some minor variations exist to the equivalent circuit that we developed on the previous slide. Consider the resistance RR prime divided by S. This is a variable resistance whose value changes with changes in speed of the machine. In practice, however, this would be a fictitious resistance, because in the rotor circuit we don't have a variable resistance. We have rotor bars or we have rotor windings, and all of them are going to have a constant fixed resistance value. So some variations to the equivalent circuit try to take this into account. And what they do is they break that RR prime divided by S into two components, RR prime and RR prime times 1 minus S divided by S. This also helps us model the resistive losses in the rotor circuit separately. So we would say RR prime is going to take into account the rotor losses, just like R of S would take into account the resistive losses of the stator circuit. RR prime 1 minus S divided by S is a fictitious resistance that would represent the mechanical load of the motor. We're not going to talk about it today. This is a topic for one of our future lectures, where we will break the motor into various flows of power and we will see how RR prime 1 minus S divided by S represents the mechanical power that the motor is delivering to the load. So for now, just consider the fact that RR prime in the rotor circuit is an actual resistance. RR prime times 1 minus S divided by S is a fictitious resistance. Let's review some of the important things we learned today. The equivalent circuit of an induction machine is similar to that of a transformer. That's because both operate based on the same principle of voltage induction. The model we develop is per phase, so you would have to convert the three-phase quantities into single phase before you want to solve the circuit. In transformers, you remember that you would have the choice to refer the quantities to either the primary or the secondary. Induction machines are different, however. The quantities are always referred to the stator side. Another difference between the induction machine model and the transformer model is the rotor impedance value. In a transformer, all impedances are fixed. In an induction machine, however, because of the impact of speed variations on the rotor parameters, the impedance is going to be variable. It's going to be a function of slip or a function of speed. And finally, another important difference between the two models lies in the shunt branch that represents the core parameters. In transformers, you remember that sometimes for simplicity, we would ignore the shunt branch in the middle. In induction machines, however, we often do not do this. We often consider the shunt branch and solve a T equivalent circuit. This is because, as opposed to transformers, the value X of M, the magnetization reactance, in an induction machine is typically small, so it's not easy to ignore it compared to the rotor parameters. Now let's do a couple of exercises related to the circuit model for induction machines. In the first activity, what I'd like you to do is to find the model for an induction machine that is running at synchronous speed. Again, I would like to ask that you pause the video at this point, think about this activity, and once you're ready, hit play to see the solution. Well, at synchronous speed, the slip is going to be 0. In the circuit diagram that we developed, the only element that is a function of the slip is the resistance RR prime divided by S. If S is 0, that resistance becomes infinity or open circuit. The model is shown on the slide. This indicates an induction motor that is delivering no power to the load. And this should make sense because if an induction machine is running at synchronous speed, the relative speed between the rotating magnetic field of the stator and the rotor circuit is going to be 0. Hence, no voltages or currents are going to be induced in the rotor circuit, and in other words, there will be no developed torque. So no power is going to be delivered to the mechanical load, which is indicated in this diagram. Now in this activity, I'd like you to find the model for an induction machine which is at standstill. Again, please pause the video at this point, work on the model, and once you're ready, hit play. If we follow the same logic, at standstill, the slip is going to be 1. Now I'm going to take the resistance RR prime divided by S, and we'll break it into two parts, RR prime and RR prime 1 minus S divided by S. If S is 1, RR prime 1 minus S divided by S will be 0. You remember from the previous discussion that RR prime 1 minus S divided by S represents the load on the machine. It's a fictitious resistance, of course, but it represents the mechanical power that the motor is delivering to the load. If this is 0, that means the load has been short-circuited. So a machine that is operating at standstill, in other words, a machine that is not running, is representing a short-circuited machine.